Let us do some simulation, circuit simulation. To do circuit simulation, we will use two open source tools. One is KiCad and the other is ngSpice. You may have heard of both. Both are open source tools, freely available, easily downloadable and installable onto your respective operating systems. I am going to use Fedora. I am comfortable with the Fedora Linux and I will download and install onto my Fedora Linux operating system. But I guess it must be easy to install even on the Windows on the Mac OS system. So KiCad is a very powerful tool. It is quite popular. In fact, you may have heard of its being used for PCB fabrication in designing PCBs. But we are going to use, for the purpose of simulation, the front end portion of KiCad, which is the circuit schematic capture part. We want to capture the circuit schematic using the KiCad's schematic capture tool, or the schematic editor of KiCad, and then convert that captured schematic into a netlist and use that netlist in a simulation engine, very powerful simulation engine called ngSpice. ngSpice is an environment. It works in an environment called Nutmeg, and it has very powerful features. It is a very large, deep program, especially for simulating circuits. It has actually three parts. The original Berkeley Spice 3F5 from Berkeley for circuit simulation, it is incorporated in ngSpice. ngSpice is also capable of doing mixed level simulation. There is this CIDER, 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 and by the extension of this CIDER being incorporated into ngSpice, you will see that ngSpice can handle mixed level simulation very nicely. Not only that, it can also handle mixed signal simulation. By being extended due to the incorporation of xSpice into ngSpice. So ngSpice has incorporated all these things, xSpice, CIDER, Spice 3F5, all those things, and it has become a real powerful package, and anybody, a hobbyist can use it, a student can use it, a professional can use it, and it can cater to all categories of people who want to use Spice for simulation. It is a very deep package. It has a slightly longer learning curve, but once learned, you can really enjoy simulating using ngSpice. So ngSpice and KiCad together gives you a very powerful team. The KiCad is used for the front-end screen capture, the circuit capture, schematic capture, and the back-end simulation engine is ngSpice. So these two are nicely integrated, and you will see that the integration is so seamless that this schematic capture to simulation is very, very smooth and seamless. So we will get to using these two packages, and I will show you, and as the examples, as we get to do the example, you will learn by doing. So let us dive into it. So now let me pull in a command window and install both KiCad and ngSpice. On Linux, it is pretty simple. You can use the package manager, and the package manager will search for ngSpice and KiCad in the repositories and install it along with the dependencies. You must have some exe file for the Windows which will set it up. I think you will find them appropriately the correct installation file for Windows and Mac OS also. So let me show what I did for my Fedora Linux OS. I used the DNF sudo DNF install KiCad. I have already installed, but anyway, I just wanted to show you the command which I use for installing. And it's updating, loading the repositories, and then it has checked that already that KiCad latest version has been installed. If it is not installed, it will install KiCad along with all the dependencies. Likewise, I will do the same for DNF install ngSpice. So in a similar manner, it will search, update and search and look into the repositories and load the install the ngSpice file along with the dependencies. As I have already installed that, you will see that this message that the latest version is already installed. So I have both KiCad and ngSpice and I'm good to go. Let me trigger the KiCad application. So when I click on the KiCad application, I will see this window appearing. So you see that here it has a schematic editor, symbol editor, PCB editor, footprint editor, and then a package which can handle the Gerber view, image converters, and all those things. For us, for now, for circuit simulation, we want to use only this part of KiCad, which is the schematic editor. So for that, let us create a new project. So let me start new project, and I will give it a name. So let us say that I create a project which is titled half wave rectifier, and I save that. Half wave rectifier. So here you see that a new project is created, half wave rectifier KiCad Pro. There are two files here. One is for the PCB and one is for the schematic. Right now we are going to be bothered only with the schematic. I will double click on the schematic. So once you double click on the schematic, you will see that the schematic editor pops up. Schematic editor, the half wave rectifier, the title appears there. So you see this mouse with this plus cursor, and you can move the mouse wheel, and kind of zoom in and zoom out. Okay, so this is possible with the mouse wheel, and there are certain operations here which we can do. So we can learn as we go along. The first thing is that we want to build a circuit. So what is the circuit that we shall build? Recall that earlier on we had discussed this half wave rectifier circuit. You have a sine source, a diode, followed by a capacitor, filter, and the load. So let us build this simple circuit and see if we are able to get the waveforms that we expect. So let us build this circuit in the KiCad schematic. Let us now go to the schematic editor and draw the circuit schematic. Okay. If you want, you can draw the title here. I can, on the right side, you see that there are several icons. Okay. First, I will choose this text icon here. So I will add text, and here I will say that I want to give the title on top, half wave rectifier with capacitor filter. So let us place it. I will place it somewhere here. Okay, so that is done. Then on the right side icons, I have here this op-amp shaped symbol is the add symbol. So if I click on that, you can now start placing symbols. So let me go to the search box and then V sign. So you can keep typing, so you will see that components appear, and this is a sine wave source I want. So let us take a sine wave source and I will place it. Let me pick all the other components also. Then I will need a diode. So I will take the default diode and maybe rotate it appropriately and place it. Then you need a capacitor. So I'll pick up a generic capacitor like this, and then I also need a resistor for load component. So this is the resistor. Right. So this forms, and you can go and pick again the normal cursor, and you can select all, move it under here, centralize them. And I can zoom by using the mouse wheel. Okay, now let us draw the circuit. Let us draw the wires. Again, on the right side, you see this icon, add wire icon. Click on that, and then you can just start connecting the wires. So connect the wires like this. It's pretty simple. It will snap automatically, so you don't need to worry about actually alignment. So whenever there is a joint, you will see that it will put a joint mark like this. So your circuit is done. Now, most important, you have to define a ground point, a circuit ground. Circuit ground is a virtual ground, and for all SPICE based simulation, a circuit reference is needed called the zero node. So we will take the component symbol and search for zero ground. So this is a zero ground. This is a zero reference. All other voltages are with respect to this node, and this node is having zero voltage. So this is very important. You need that, otherwise the simulation will not perform properly. So connect it. So this becomes the circuit ground. So with respect to this node, all the other voltages will be measured. Now let us put in some value to the parts. V1 is the sine wave input. So if I double click on that, if I double click on this value part, so you have DC value. I don't want DC value, it's a AC sine wave voltage, and let us say 325 volts. 325 volts. Frequency of 50 Hertz. 50 Hertz is our frequency on the Indian grid. So let us set that like this. So you see that it appears here. Now this diode is a default diode. If you actually click on the diode and double click on that, you see that the reference number is D1, the value is D. So I am just, or you could have value, you can have any other descriptive name for value which will indicate the model that it has to look for. And then footprint and all those things. Right now we are not designing the PCB, and therefore I don't want to right now bother too much about the footprint value. This value I may have to bother about, but right now as I am using default diode, this I can just leave it as D. Close this. Then for this component, so let's say capacitor, I can double click on that, reference is C1, and value let's say 100 microfarads. Microfarads. So you can type it as UF, lowercase u and f, to be more descriptive. It will take it as, PSpice will interpret it as 10 to the power of minus 6. If I use lowercase m, it will interpret it as 10 to the power of minus 3. So this would be 100 microfarads. And then for the resistor, I could put in some value, 100 ohms, let's say. So this is 100 ohms. So you have all the parts here. Let us save this, save. So the schematic is saved. How will I simulate it? First, you will have to generate the netlist, and that netlist will be taken by ngSpice to simulate. So I can go here and choose export to netlist. So I will choose export to netlist, but when I am exporting, I want to export it as a SPICE model. Click on SPICE here. SPICE, export netlist. It will save, all netlist is saved as .cir. So in that same folder that we created the project folder, the half-wave rect.cir will get saved. It is a text file. We will open the text file and then see. Now that netlist is generated. So now let me go to the this one, file browser. Let me go here. You see that half-wave rectifier.cir has been created. This is generated. These are all the files generated by KiCad. You have to remember two things. KiCad Pro will open the project file. KiCad schematic, if I double click, even if I close the schematic, if I double click on KiCad_sch, it will open the schematic file. So let me double click on this rectifier.cir file. So when I open this, it will give you the netlist. So this is .title, this is the comment line, KiCad schematic. Now there is a dot model. Now let me have the schematic also with me. I will push it. Yes. So you are able to see the schematic here. So V1. So V1 is this block which is between this node and this node. See that it assigns a node name or a net name. This is net underscore hyphen underscore D1 hyphen A underscore, like that. And we have defined this net as the reference net or the reference node, which is the 0 node. So therefore it is going to indicate as 0. Then its DC value is 0, then sine value 0, 325, 50 Hertz. It's a AC signal. Now that is this. If you take the diode D, D is between this net and this net. It has assigned the two net or the node names and given a value D1. So the value is D1 here. And this D1 is the model that it will look for. So dot model, whatever you have the model name associated here, that is the model name, and for that model name we have right now a default diode model. Just D or D within parenthesis is a default diode model. If you are having specific diode models, you can incorporate it here. But right now we will not bother about that. Let us take the default model or the generic model. Then C between the net here and ground, between that and this ground, 100 microfarad value. And R is between the same two nodes, 100 ohms, and then end, dot end. So this ends the circuit schematic. So here there are few things that you need to note. The net name or the node name, they are unreadable. They are self-assigned, of course, unreadable. It's difficult for you to later on visualize or even call upon for plotting the voltages or the branch currents. If it is better to give some meaningful net names or node names. Okay, that is the first thing that we will do. Okay, so let me go to the schematic. I will choose this. Labels, you can add these global labels. I will choose that. So first is the output label. I will just give it as O and label it as output, and I will place it there. And one more at the input side. Let me label it as A and rotate that, and I will paste it here. Then use the wire. I will pick the wire icon from here and I will join that label to this and the label to this. So you see that what is it that we have done? I have given the net name for all the wires that are connected to this as A, all the wires that are connected to this as O, and all these wires which are connected here as 0. So now all your nodes are very well defined and easy for you to recognize and even call upon while plotting. Now you just save it and then again recreate the schematic netlist file. Let me go to export netlist. Spice is chosen. I will export netlist as the same file name. Now it is done, right? So now let us load that. Now you see that I have loaded this half-wave rectifier.cir. You see the net names. The net names have been defined according to what I want it to be. Between A and 0, I have the source. Between A and O, this is A and O, I have D1. Between O and 0, you have C1. Between O and again 0, you have R1. So now I have well-defined node names, which I can recall and then use it later for plotting the voltage waveforms at different points. Now I need to execute this circuit in ngSpice, and I need to have some analysis defined. So how do I do that? Let me come back again to the schematic, and from the right side menu icons, I will pick this add text icon. Add text icon, and here I will type in some commands called the control statements. Now these control statements, I will place them in between a dot control statement and a dot end C statement. Between these two, I would like to place the ngSpice control statements. What are the control statements? I would like it to do a transient analysis. So let me type in tran. Tran is the command for transient analysis. In steps not exceeding 1 microseconds, up to 100 milliseconds, 5 cycles. 50 Hertz is 20 milliseconds. And therefore for 5 cycles, I have just put in as 100 milliseconds. And I will say UIC, use initial conditions if they are there. So I just put this one. Then I will ask ngSpice to run this command. And then let's see what happens. Okay, I will close this. I will place it somewhere here. So now if I save and export this schematic as a netlist, these control statements which I have typed here will also come into the .car file, and that will be useful in ngSpice for executing. So let us see what happens to the .cir file, circuit file. I am saving and exporting the netlist, Spice netlist, export netlist as .cir, save it. So the netlist is exported, and when I look at the half-wave rect.cir, what are the changes? You see that there are some changes here. These commands, whatever is typed in the text block there gets included. So this will ensure that in ngSpice, as soon as you open ngSpice, this will execute this transient analysis given these parameters, and the results are available after the execution of the transient. It's up to you what you want to do. Okay. So now let us go to the command line. So ngSpice, as I said, is command line based, and we will open a terminal block. Let us open a terminal window, and I will place the terminal window in the center of the screen here like this, and let me go to the folder where I had created half-wave rectifier project. So this is the project. So these are the files, and you see here half-wave rect.cir, and that is what we want to execute. So we will use ngSpice. We have already installed ngSpice, and therefore I can directly call it ngSpice. The circuit file has half-wave rect.cir. So you call the circuit file. So you see that it will call and execute it, and you have so many data rows. You have around 10,000 plus data rows here. So you could also see what was executed. You can use the command listing. So let me clear the screen. Listing. If you put the listing, it will show the circuit listing. This is the circuit that you see. This is the circuit that is taken into ngSpice environment, and it is there in the ngSpice environment. You see, this is the environment prompt, and till you come out of the environment prompt, it is available to you. And now that it is executed, let me plot. What do you want me to plot? I want to plot this node voltage and this node voltage, input and output. So let's say plot V naught and VA, the input. So when you plot that, you see that you have a dark background screen appearing here, and something like an oscilloscope, and you have the chart here and then the plot. So the blue is VA. So this is the sinusoidal, goes up to 325, and this is sinusoidal AC. We had given the end time as 100 millisecond, and therefore it is 5 cycles. And V naught is the output voltage across the C filter. So you see that it charges up in the first cycle, then falls down, discharges into the load R naught till the next cycle comes into play. And we know, and we have seen this waveform, and the waveform is as we had estimated it would be, as we had predicted it would be. This is V naught. So there are few tips and tricks I will tell you to do in the schematic such that you get a much neater plot. First thing is that I would like to have the plot in white background and dark foreground. Now that is good even for copying and pasting it into your documentation, and also for taking printouts. So let us see how we go about doing that one. So let me just go back to the, I'll go back here. Okay, there are few ngSpice commands which you can invoke. I'll say set color 0 equals white. So color 0 is a background color, and I'll say set it to white, right? And set color 1, which is a foreground color, to black, and it will set the foreground color to black. And now let me plot V naught and VA. So if I plot that, you see that I will get a plot out that is more amenable to being used as a picture in a document, and also can be printed out because you will not waste too much of ink. In fact, you can include these statements in the control statements in our schematic, so that every time you don't need to remember, every time you call this CIR file, this setting for the image or the plot foreground background is already pre-done. So let me go back to the schematic, and I will double click on this, and here I will incorporate that command, set color 0 equals white. So the comment is set background color to white, then set foreground to black. What it means is set foreground color to black, and I save it. Let me save that. Then let me export the netlist, spice, export netlist into the same .cir file, and you can see that the control statement is already having that. So I could also go one step further. Let me go to the schematic and say that my opening plot, let me define my opening plot. After this, let me also plot V naught and VA. Let me start with that. I will save that. Plot V0 VA, save, export netlist into SPICE format, export netlist into the CIR file. So you see that within the control statements, within the dot control statements, plot V0 VA is also included. So when I execute this, you will see that this will execute a transient analysis, run that, set the background as white and foreground as black, and then also make the initial plot V0 and VA like this, and then leave it at that point. And further from there on in the environment, you can plot anything else also and then see. So let us execute this and then see. So let me go back to this ngSpice environment. I will exit from the ngSpice environment. Type in exit. So it is now exited. We are now out of ngSpice. Now let me run ngSpice. Again half wave rect.cir. This time it will execute, change the background foreground, and place the V0 and VA input wave shape. So execute that and then all this all at the same time, so that you don't have to repeatedly keep typing in several times in the command window in the ngSpice environment space. So this is how you get started using the schematic editor, and from the schematic editor generating the .cir file, that is circuit file. From the circuit file, go to the command window, execute it in ngSpice to see the wave shapes. Let us see how we can now measure the current through a branch, the branch currents. So let us say that we want to measure the current that is drawn from the input source, the current that is flowing through the diode here. So let me move this up, make some space here. Let me delete this wire, and here I have to introduce a current sensor. By current sensor I mean it is nothing but a voltage source. You use a voltage source having zero value. That will become a current sensor. So let me go to the symbol addition. Let me choose that. Yeah, but carefully place the voltage source in such a direction such that when the current is flowing into the positive terminal, the positive current flows into the positive terminal of the source, voltage source. So that's how you should place it. And now let me change the cursor, select that, double click on that. The value is 0. The value is 0, and all this is 0. If you want, you can hide this. Show. I can hide that. Sim params, I will hide that so that it is neater. Move that closer here. Yes. Now this becomes a current source. I will go and pick the wire symbol and connect this up. I will connect this up. So current through V2 will give me this branch current. So wherever I want, I can put a 0 voltage source and use that one as a current sensor. So let me say I want to measure the current through this branch. I can go here. I will also include one more, which is I, current of V2. Current of V2 will give me that. Let me left align it. Yes. Yeah. So here you have IV2 also being measured. Now let me save this, export the netlist as spice netlist into a .cir file, save. Okay. So now let me open that half-wave rectifier.cir. You see here that I am going to also display the current that is flowing through V2, which is actually the current, that is the branch current flowing through the diode D1, which is also the same as the one which is flowing through the source, the input source. Now let us execute this. Let us run this. So let me open this. Let me come out of the previous ngSpice session. Let me clean up the window. I'll say ngSpice half-wave rect.cir. So when you do that, now you see that interesting IV2 shown as yellow here. So you see the current wave shapes. You can, if you want, you can amplify them. You can right click on that and make a box, and then you can amplify that box. Okay. So you will see the current wave shapes that is flowing through the diodes. So these current waves. So in this way you can actually visualize the voltages and the currents of any part of the circuit through simulation, get an insight, understand about the circuit, and try to design the same. Now I would recommend that here when you are placing the components, you use generic components, because you may not know the ratings. Only after you have completed the simulation, probably, you can look at the waveforms and then come up with more precise ratings for the diodes. For example, if you look at the diode waveforms, you see that the diode has to withstand the entire input wave shape potential. For example, let us plot the voltage across the diode. What is the voltage across the diode? Let me do listing. So the diode D1 is between a net and this and A. So there is a in between net here. I want to, let us say, see the voltage from here to here, because this is going to be 0 volts. And effectively I will get the voltage across this diode. This is node A, this is node 0. So let us plot that. Plot voltage node, if I want to see A, comma 0. Then you will get the voltage across the diode. You see that when the diode is conducting, it is 0. then it has to withstand the voltage. So it is withstanding the reverse peak 325 and also the voltage, that is the capacitor voltage in that loop, right? The capacitor voltage in this loop, and then you have the reverse voltage appearing. So the diode needs to withstand all this negative voltage, the peak inverse voltage. The peak negative voltage of the input, which is 325, and a plus minus voltage of the capacitor at that point in time, those two add up and then appear across D to give a maximum of 450 volts, minus 450 volts. So what is the voltage at this time? Across the capacitor? You can always look at that. Let me make this smaller. Let's say I will say plot VO. So I can place it underneath like this and compress it like that. So you will see that at the time when it is max negative, it is somewhere around 100 plus voltage. So 325 plus 100 plus, so around 425 to 450 volts. So that's what you can expect. So you see that you can kind of validate, corroborate what you think must happen and what you think is happening, and check the waveforms at any point in the circuit, or the current through any branch in the circuit. So this will really develop great insight into the circuit, and also it will give you an idea that what should be the value of the diode rating. So we normally design that, okay, this, if the ripple is small, then this will be at 325 and the minus 325, so 650. We say 650 should be the rating of the diode. That's how we went by theory. But if the ripple is large, then you can even bring down the rating of the diode because the max value is still lesser. So these are things that you can actually play around with and really get a feel for it. So you can actually see what happens when the load resistance or changes. So you can sweep the load resistance and see what happens to the output. So these are things that you can try out with ngSpice and try to get a much better feel into the operation of the circuit and the various components in the circuit. You can also plot the waveforms on a single graph like this, comma and V0, so that you can see them together and convenient to take measurements. I want to show you something important here now. Next, let me close all these plot outs. We go to the schematic. So what happens if I vary C1? So you would like to see the waveforms when you change the values of C1 or change the values of R1. When you are in the ngSpice environment, you can do parametric changes. So that's what I want to show. Let me go back to this. Let me clear up the screen and let me list. So this is the schematic. Say for example that I want to change the value of C1 from 100 microfarads to 1000 microfarads. What is the effect? Okay. Before that, one command in ngSpice, set plot. So just if I type set plot, it will give me what are the available plots. So the current plot, it has done one transient analysis. It has auto named it as tran1, and then there is constants. Okay, so data related to the constants. So this is probably the plots that we saw just now, outputs and across the diode corresponding to these parameters. Okay, now I will want to alter the parameter. Okay, I will type alter C1 to 1000 microfarads. Right? So you can type this on the ngSpice command prompt, alter C1 1000 microfarads. So now that it is altered, I will run another transient simulation, tran 1 microsecond to 100 millisecond UIC. So I will execute that one. So with the altered value of C1, this has been executed. Where you can see, again I'll say set plot. So you will see that there is a second analysis that has been performed, and there is a first analysis tran1 which already was performed, or is existing in the workspace, and you can utilize that accordingly. So let me clear up the screen, set plot, so that you see this tran1 and tran2. Now I want to plot. Now I want to plot V0 of tran1 with C1 as 100 microfarad and that corresponding to tran2, where C1 is corresponding to 1000 microfarads. So let us plot this. So from tran1, I am going to take V0, and from tran2 simulation, I will also take V0. But only difference is here the capacitance value was 100 microfarad and here the capacitance was 1000 microfarads, and I want to see the difference. So you see them together like this. So you see this red waveform is from tran1, and we saw that the ripple was larger because the capacitance value is 100 microfarad, lower value, compared to the blue plot, which is corresponding to C1 of 1000 microfarads, and you see the ripple is correspondingly lesser. So you can really get a lot of insight by playing with the parameters or the variables and plotting them together, and then seeing what happens in the circuit for the various voltages and the branch currents. So I'm just showing to you one of the powers of ngSpice, especially when you want to modify the parameters and evaluate what happens.